Sorry, getting a little late start here. Got bogged down by some students after my last class. So today we're basically going to be going through just a lot of the topics we talked about last week, and we may then start to do a little bit of review over stuff that we covered earlier in the semester. So let's see here. Why are these not showing up? Well, oh, is that not in? I'll open. Should be on my OneDrive. They're in week 6. Okay, so we'll open this up. Kind of scroll down here. We got through, excuse me, we talked about the, or we looked at that powerlifting data set last week, correct? So I think that was the example we kind of left off on. I'm not sure we went through all this, so I'll kind of revisit it. So we'll kind of pick up with that example. But we're going to be talking about kind of the issues related to multiple linear regression. So let's go here and open up that data set. So I think it was that powerlifting kind of data set here. They had this multiply variable that we generated. We'll talk more about that in a second. I wanted to kind of make a point down here though. Okay. So a couple of things that we had talked about was when we're looking at these different regression models, we can kind of determine whether or not adding in additional variables. We can look at the individual significance of each variable. We can also test for the joint significance if we're adding in multiple variables. So I want to talk through a few things here. So there we go. Is that, oh, there we go. So we had our F statistic, which was going to be our R squared in the unrestricted model, the difference between that and the R squared from our restricted model. So we said, anytime we're thinking about a sample statistic, we can turn it into a test statistic. So this is as simple as, when we looked at one slope coefficient, we just took that slope coefficient divided by its standard error. That gave us a test statistic coming from a student t distribution, right? Now, another way we said we could think about this, it's kind of like it's the standard error of that sample statistic we're estimating. Same kind of idea for our F statistic. It's still a test statistic. It's just coming from an F distribution because we know when we add in multiple variables at a time, what has to happen to our R squared? It's going to increase, right? So the sample statistic we're actually interested in, it's kind of like the change in our R squared. Now we have to write that out because to calculate the change, we need both the R squared from our unrestricted model and the R squared from our restricted model. Okay. Now, what we were going to do here before in our standard error, there was this equation where we had kind of this n-2. So we only had degrees of freedom, this n-2, kind of influenced by our sample size. That was only going to be impacting our denominator. We're now going to be dividing the numerator by something. So we're dividing the numerator by Q, which, do you remember what Q represented here? So this was going to be the number of variables, essentially, that we are including in our unrestricted model that weren't in the restricted, right? Or the number of variables in our new model that has more variables compared to the one where we only had a smaller subset of variables. So this is we call this the number of restrictions, or it's basically just the difference between the number of variables in the two models. Now, this is where I saw some confusion. People stopped by office hours. In the denominator, what we're going to be dividing this by, right? We can kind of think about, this isn't technically correct, but to calculate any test statistic, we're dividing by some like standard deviation. This is kind of like the standard deviation for the change in R squared. It's not technically quite what it is, but that's an easy way that's a good way to think about it, right? So here in the denominator, I take 1 minus the R squared from my unrestricted model. So when we say unrestricted, that's the model that includes all of our variables, right? So this is the one that kind of you would run usually second, right? This was kind of our second regression that had additional variables. Then just like our standard error for our slope coefficient, we divide this by not n minus 2, but we said n minus k minus 1. So k was the number of variables in the unrestricted model, right? So I saw a lot of people kind of working through the problem set or thinking about the quiz. They were using the R squared from the restricted model that denominator, not the R squared from that kind of model that leaves out variables, or sorry, R squared, okay, the same thing. But it's not the number of variables in that regression that leaves out some variables. It's the number of variables in like our full model, the one that includes every single variable that we were kind of testing that joint significance of. Okay, so here we'll kind of work through some examples where we'll think about what's going to influence this test statistic. Okay, so we'll go back here, and I'll add some stuff in that wasn't in this data set. So let's say, I'm going to zoom in a little bit so you guys can see this a little bit easier. There we go. So let's do. So I think what I was doing last class a lot of the time, just to kind of prove to you, this would be what we would call our restricted model, right? It's leaving out these additional two variables. So this is where we're trying to predict the total weight lifted from someone's body weight, whether or not they're male. And then we have these additional variables. We said, are they jointly significant if we add them into our model of age and raw? The same jointly significant. Another way of thinking about this is, are they allowing me to make better predictions, right? Or are adding these variables in my regression, is it allowing me to explain more of the variation that exists in that Y variable? Okay, so we can run our restricted model and our unrestricted, right? And if we do that, let's see, can we get this all on one line here, or all on one screen? We now have the output. We need to calculate that test statistic, right? Because what did we need? We needed our R squared from the restricted model, so that was 0.6539. We need the R squared from our unrestricted model, 0.6939. We also needed the sample size. Now, here, any example I'll give you, like on a quiz or an exam, is going to have the same sample size as both, right? If I give you the problem set too, I'll clean it up so that's not, we're making sure we have the same number of observations for both. What you don't want to do is sometimes when you get some like raw data, maybe it has like some of the observations had information on body weight and male, but it didn't have information on age, right? So you might end up with more observations in your restricted than your unrestricted model. So we don't want that to be the case. When we're comparing these models, it needs to be the same set of observations. So as we have here, the same sample size. We also could get the number of restrictions. So our number of restrictions here was what? How many variables were in that unrestricted model compared to the restricted? So body weight, male, age, raw. So we have 4. How many were in the original one? Just body weight and male. So our number of restrictions is 2, right? Also, did I start recording this? Yes. Okay. Just making sure. So we've got Q now. What was the only other thing we need? We need that K, number of variables in our unrestricted model. So here K would be 4. Yep, there's 4 variables in that unrestricted model. Sorry, excuse me. So there's some kind of tricky stuff going on here. But if we think about when we're looking at this test statistic, we had everything we need to calculate it. Right? So we're going to do this when we have 2 restrictions. I'm going to think about some other variables I can add in. I don't know which ones are going to be yet. We'll kind of ad lib it, but I'm going to try to end up with 4 restrictions. Now, notice what's going to happen then. Here, I'm going to have a larger K value as well. So this, dividing by a larger number, what's going to happen to my fraction in the numerator? It'll get smaller. I'm subtracting a larger number here, so this is going to be smaller. I'm dividing by a smaller number. My denominator is actually going to get bigger. Both of these things should do what to my test statistic? If the denominator's this entire denominator is larger. My numerator is smaller. It should make it smaller. Right? Now, let's see if this plays out and talk about one caveat to this. So what we can do in Stata is we don't have to run this restricted, unrestricted, do the calculation by hand every single time. I might give you that output and ask you on a test and make sure we know like what the actual test statistic is testing for. But we can run this test command and then just say, okay, from the unrestricted regression, like let's say it's the only one that we ran. We can then use that test command. It'll run the restricted model in the background. So it'll run that same regression without age and this kind of raw identifier, which is they have no assistive equipment when they're making these lists. And that should spit out at us this test statistic. Right? Now here, when you have a really large sample size, we said we ended up with a really large test statistic. Right? So if I run this regression, I get a test statistic that's like in the thousands. My p-value is definitely going to be 0. Excuse me. Sorry, I'm just getting over being sick from this weekend. So just to kind of reiterate this point, and it doesn't really matter here. I probably could have just written this whole thing out. Wow. So what I really wanted to make a point was, why does having a high sample size make it very likely I'm going to get a high test statistic? Well, these sample sizes really shouldn't influence the number of restrictions, but what it is going to influence is down here, right? So if I'm dividing by a larger value here, what's happening to this fraction? I'm dividing by a number that's smaller, that's going to drive my F statistic way up, right? Which then leads to my p-value being what? And am I more or less likely to reject the null? Small p-values, less likely to be what? Less likely. More likely to be less than alpha, so I'm more likely to reject. Right? So we kind of see that play out here with that large sample size. We get a really large test statistic and a really small p-value. Okay? Now, it doesn't show me the restricted like output. It kind of just keeps all of that behind the scenes. So I think last class, I don't remember if I quite got to this, but if I instead were to use a smaller sample and do this exact same test, so this code here just generates some random numbers, and it randomly selects 100 of these observations. So my sample size is now getting much smaller. So instead of having a very large test statistic, my test statistic is going to be smaller, and I should see a higher p-value. So if I run this regression where I'm only using a sample size of 100, right? Sure enough, my test statistic is quite a bit smaller. Same data, right? I'm still sampling from the same population, but I have a much smaller sample, right? I still would kind of find a pretty similar difference. I'm looking at my restricted R squared there, 0.69 compared to 0.69. Like it's a little bit off of the third decimal, but I'm finding basically the same R squared values. But because that sample size is so much smaller, I'm going to end up with a lower test statistic, right? And that's just based off of kind of the way we compute that F statistic, and the fact that we know, like, yeah, I found the same R squared values, but it's coming from fewer observations. It's more likely that I ended up with observations that were in the tails, right? It's just more likely if I only have 100, I end up with some really extreme values that influence that, as opposed to I have 84,000. Well, yeah, I also have some of the extreme values, but it's much more likely I get most of the values in the middle of the distribution. So here, we actually end up with a case where if I have smaller sample size, even finding a pretty similar R squared to my restricted, unrestricted model, I actually end up failing to reject. Just kind of highlighting this importance of our sample size. I then want to think about, okay, well, what if I went back and did this exact same? We'll use the smaller sample size because I think the values will really cause a pretty big difference. So let's say I want to do the exact same thing. So I'm going to copy and paste this. Right? But instead of just these additional 2 variables, which ones am I going to include? Let's see here. Well, we haven't talked about this yet, but we'll allow age to not just be linear. We're going to kind of throw in this age squared variable. I'll also throw in this variable of kind of wraps, right? So age squared and wraps was kind of a 1-0. They allowed some assistive devices in these units. So I'm going to run this regression. Oops, I've now got 4 variables I want to test for the joint significance of. So we said, if I instead have 4 variables, it's more likely, it's going to decrease my numerator, increase my denominator. It's going to decrease that F statistic. So I'm more or less, skipping a step. What's going to happen to my p-value? Smaller test statistic, larger p-value, I'm now less likely to reject. So now if we run this regression, we're testing instead 4 different restrictions. Relative to before, okay, well, I'm still using that small sample. I'm now testing 4 of these restrictions. I actually end up with a higher test statistic and a smaller p-value. So why could this be the case? Well, let's dive into this a little bit deeper. So instead of just running this restricted model behind the scenes, let's actually see what the results are. And then down here, same kind of idea. We're going to look at the restricted models results as well. So we'll go here. Oops. Get rid of these 4. Okay. So if I looked at the restricted and unrestricted model before, when I only had 2 restrictions, right, my R squared was 0.6759 to 0.69. So I know it's about what? 0.015 was that change in the R squared. So we're kind of keeping track. In our model that had 2 restrictions, that kind of difference between our R squared from our restricted, unrestricted model, this was about 0.015. Okay. When Q is equal to 4, let's see what happens when we run this restricted and unrestricted model. Well, hopefully we get the exact same R squared from our restricted model, because it has the same 2 still has that body weight in male. So 0.6759. But now what's the R squared from my unrestricted model? It's went up to 0.73. So now I'm looking at a difference of what, about 0.055. Right? So here, that gap in my R squared, when I include these 4 restrictions, was much larger. Right? So it is true that adding in more restrictions is going to have some downward pressure on your F statistic. But remember, when I'm adding more variables in, what is it more likely now? I've added in variables that are really good at explaining that Y variable. Okay? So it must be that allowing age to kind of have this age squared, not to just be linear, that's something we'll dive into after this exam. But also adding in this assistive equipment, kind of whether or not they could use these wraps, right? Apparently that was much, we could explain a lot more of that Y variable. So yes, the number of restrictions will make it less likely we can reject the null because it pushes that test statistic down. But if adding in those additional restrictions, we've increased that change or that difference we see in the R squareds, that's going to cause our F statistic to go up. Now it kind of starts to look at like basic microeconomics. When you had like sine, if you go all the way back to 371, or if you took 251, if you start out in Kelly, we have demand and supply changing at the same time. Sometimes things are indeterminate. That's what we have here. When we add in more restrictions, that's going to cause us to be less likely to reject the null, see lower test statistics. But when I'm adding in more of these variables, it's more likely I also see that this gap in the R squared is going to increase, and that can sometimes offset that, right? So in this case, we can kind of see with that R squared, it went from like 2 something to like 4.6. So it must have been that, yes, we were penalizing ourselves from now having 4 variables we wanted to test the joint significance of, but those additional 2 variables we added must have had a lot more explanatory power. It was really causing that gap between R squared to go up, and so we end up seeing a higher test statistic. Right? And we can kind of say, if we're thinking about what our rejection decision is here, at any conventional level, the p-value of 0.0018, we can definitely reject the null. What's the null here? That all 4 of those included variables had no effect. We're saying here, when we add those in, they have joint significance. Any questions? Yeah.
Yeah, so, real quick about the null hypothesis, is that always our null hypothesis when we're testing for, like, when we're doing regressions, like, the null is that these things have nothing to do with each other, and we're trying to find, I know it might be like.
No, yeah.
Back.
No, you're right.
I've been.
So we're always starting out with these, even if we do individual significance. So if I'm looking at those p-values associated with each individual variable, what are we always assuming that slope coefficient is?
So 0.
Zero, there is no effect. What are we assuming here? That adding in these additional variables, no effect, right? So we're always going to stack the deck against ourselves. We're assuming that nothing is going on, or that there's everything's zero. Now, the one exception to that would be when we test for heteroscedasticity. We're saying that the variance isn't equal to zero of our error terms, but the variance is constant, right? So it's, you know, that's not quite saying they're equal to zero, but we start out assuming we're trying to see, do these things have an effect? We assume they don't. With heteroscedasticity, we want to see, is there heteroscedasticity in my errors? I assume there is.
So you assume it's always good.
Yeah.
So that's why you assume it's constant, because if you were to draw a line of best fit, you'd say that like the upper and lower values have constant values that are between them, right?
Exactly, right. That variation in our errors is the exact same no matter where we're at.
Gotcha.
Yep. But just the general theme is our null hypothesis is always like whatever we're trying to find. I think if you go back like 370, I always try to phrase it this way. Whatever you're trying to test for, like whatever you want to try to find, you assume the opposite is true and stack the deck against yourself. So if I think there's heteroscedastic errors, I stack the deck against myself and assume they're homoscedastic. If I want to find whether or not these variables have joint significance, had an actual more, could explain more of the variation why, I assume that they did. Yep.
Yeah, that's sort of rudimentary question, but like when you get
No.
into the nuance, sometimes.
No. Sometimes like you get further into this, like it's good to like go back and remember like where did we start? What was the basis of this, and like why are we doing it this way? It kind of helps kind of reset it up, I think. So these are good. So today, Thursday and Tuesday, I have no new. I mean, I say no material. I have examples I'm going to run through things I think I want to do. This is really for you guys. Like I want you to ask questions. Like this is, this should be a lot more kind of Q&A. Asking me, what's this going to look like if you ask this in the exam or things like that. Like we've already worked through every topic that we wanted to cover. It's just kind of rehashing things.
Excuse me. So what else did I want to say there? I think we're good. Let me see here. Oh, just to kind of make a point about some things that we also had done earlier, and I think this shows up on the problem set. So, actually, let me bring something up as I'm thinking about problem sets. So, and maybe I'm talking to the wrong group because you guys are all here. I'm guessing this is going to be people that have been relying on the recordings of this and things. So, I can't remember. I think it's HTT test or H test. Let's see if this. I'll do it up here. I think this is what it is. Yeah. I think that's the command people are using because I don't think this one will do anything. Yeah. So I appreciate the
effort to go out and Google and look for how you do things in Stata. Anything that I ask you to do should be something that's in one of the do files I have posted on campus. In fact, often there are other things you can do, but they're not going to be exactly the same. And if you just go out and Google it, it may not be obvious to you that it isn't the same, right? So we've only ever used the test command to test its joint significance, right? So I've kind of seen some people kind of thinking about, and this actually goes back to not joint significance, but just where tests like heteroscedastic. This HET test, right? So when we wanted to test for heteroscedastic errors, I kind of had a way that I showed you how to do that.
So if we go back, let me see. I think this was going to be in the old. Oops, not new. I wanted to open. So let's see here. This would have been week 5. Yes. So let's see. We've got multicollinearity. blah, 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 blah. Oh, maybe it was in week 4. It was on the last problem set, so I know it came from one of these two. So let's see. Where's my heteroscedastic? Oh, we might not have done this. Nope, sorry. I should have had this planned out. I just thought about it off the top of my head, though. I think it's in this one. Independent, blah, 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 blah. Here we go. All right. So we had talked about kind of using this SStat IM test. So I'm gonna run it in the one that we're using today. So we had inference. So SStat IM test. And I'll just kind of do a really basic regression to kind of make this point instead of doing several. All right. So let's just say we're running this very basic regression. We're trying to predict total weight lifted by body weight. Right? So I'm going to run the regression, and then run this SStat IM test. Oh, I don't have the syntax right. What is it? Oh, I don't need to. I only have one variable. So we just run this, right? So it kind of gives me these different tests. One of them is kind of heteroscedasticity. So you see here, it's like squared value. We talk necessarily about the test statistic here. We just said we're focusing on that p-value output, and we'll say and p-value 0, right? Well, essentially, this is my test statistic for that test of heteroscedasticity. A lot of you, I think, Googled and found this HET test, right? So notice it gives you a value, and it's similar, 5,900 instead of 5,000. So with large sample sizes, it might not cause a difference in your rejection decision. I think the data set I give you on the problem set number 2, though, it did lead you to make a very different rejection decision. I didn't show you this one in class because it's not quite the type of heteroscedasticity test we talked about in class. In fact, what it actually does, and it kind of tells you here, excuse me, so this Baruch, Hagen, Cook, Wiseman, it's actually running multiple tests and giving you like an average across, I think it's 3 different tests, right? So one of those tests is that one that we were using an IM test, right? But these other methods of testing heteroscedasticity, we hadn't talked about them in simple linear regression. We shouldn't have been using. They're not quite doing the thing that we were talking about in terms of the heteroscedasticity that exists in the error terms. So it's great that you're going out and trying to find like how to do things, but sometimes you're not, you go out and find it, you're not maybe able to identify it's not the exact same thing as the test command that we were running in class. So anything you use in those problem sets should be coming from somewhere in the view files that we use in class, right? Otherwise, you might be doing a slightly different test, right? You end up with a different test statistic here. Now, in this case, the p-values are both 0, so it wouldn't really matter. Like in the problem set, I think if you use this kind of compilation of multiple tests, this HET test, so that's what it does, you actually end up with a p-value that was significantly different than using that IM test, the Cameron and whatever his name is, the composition. I'm going to try it with the Trevelyan. So you'd actually end up making the wrong rejection decision, right? So what I'm actually going to do, because I'm feeling nice. So my GA that graded them didn't grade yours if you did that. I'm going to go through and then grade them based off of grading it correct, based off the p-value that test gave, right? So if you use that test, I'm just going to grade it accordingly to that p-value, not the one that kind of came from the other test. But kind of moving forward, you should only be using kind of these tests or this code that we're using in class. Okay? A lot of the time, this is like a little more complicated. Right? We're looking at the amalgamation of like several different tests. So I digress a little bit, but I wanted to kind of bring that up. Excuse me. So another thing I wanted to bring up here today. So if we come down here, I'm going to kind of not worry about, well, we can kind of go through all those. So this should be hopefully pretty easy. So I have these 3 different categories, right? One was kind of a raw, right? 1, 0, 3 dummy variables. There's 3 different types of power, right? One, no assistive equipment. The racks, you have some light assisted equipment, and this multiply, which is really assisted equipment. So it has to be categorized in one of these three areas. So if I try to include all of these in my regression, well, anytime these two are 0, this one automatically has to be 1. There's no other type of meat. There's only 3 different types here. So if I try to run this regression, notice we said Stata will do what? It kicks out one of my variables, right? So here it's going to kick out, it chose to pick out this multiply, and that's fine, right? We said in general, what group do I want to probably try to leave out? Either the lowest or highest. So this one, it looks like the other two, okay, the predicted weight lifted is actually lower in both, right? So this would be an okay one to leave out, right? Because I can kind of see here, oh, it must have had the highest average weight lifted relative to the other two and the types, right? The other two categories. Now, if I had asked you here, what's the difference in the predicted weight lifted from these meats that allowed wraps versus the ones that were considered raw or no assistive equipment? How would I find the difference between those two categories if this is the only regression I had? Yep, right? So when I'm making these predictions, you can kind of think about how am I making these predictions? Well, you know, let's assume we're looking at the same lifter with the same body weight. They're either male or they're not. They're both the same age, but the only difference is one of them was kind of in this raw meat category. One of them is in this kind of wraps meat category. Well, the predicted value would be the exact same. The only difference is I'm adding in that raw coefficient to one, I'm adding in the wraps coefficient to the other. So what's the difference between the predictions? Just the difference between those coefficients, right? So I can always still get the difference between any two groups. Now here I only have 3 groups, right? I think maybe in problem set 3, I gave you one where there's like a ton of different groups, right? Like education, like there's like 6 different categories. So you can only ever leave one out, and it's not really valuable to like kind of rerun this regression 6 different times to make all these comparisons. We can always compare any 2 groups that didn't get kicked out by simply looking at the difference between their coefficients. Yeah.
Can we go for why? Why, like I know it does, but why is it the highest or lowest?
So it actually, I don't think will always leave out. In fact, let me try to do something here real quick. This might not like this, but we'll try. So let's say I do total kilograms, body weight, kilograms, male. Here. Not contain, oh, what is age? Oh, come on. Let me think what's one I could do in this data set. Oh, let's do. That's not fun. I'm going to cheat. Round up. I have to remind my, oh. Okay. Oh, I forgot my equal sign. Gen, because I'm calling this. Oh, it is round. Okay, never mind. I say I thought there was a round function. Unknown gen function. Okay. Let's make sure that did what I wanted it to do. Now,
Just rounding everything.
yeah, now I forget what the syntax of round is. So let's go back here. Round, oh, I have to type. Okay. Let's go. I want to round age, the nearest integer. I'm going to drop that old one that I created. There we go. This should do what I want. Yep. Okay, so I've rounded age. So now I should be able to run this regression. Sorry. Because I don't need to use the old one. I now need to use the new variable I created. There we go. So this is kind of crazy, right?
But basically, this, using this IDOT command was a way we could have, or include a dummy variable for every single possible response. So now it's like every age has like their own dummy variable, right? It's including them all.
Now, if I look at, so this goes all the way up to 65. So if I tab the actual age variable, I think the lowest was 18. Notice it's excluding one of those ages, right? It's not including that 18. So that's kind of like my omitted group, right? The reason why I have to omit one of those groups is because the interpretation of each one of these coefficients would be, here's the predicted increase in weight lifted if the individual was, say, for example, 30, relative to, well, these are all dummy variables. So we have to have a zero group. If I included 18-year-olds also as a possible group, I now have included every single possible age, there's no comparison. So the reason why I have to leave one out is because if I didn't, these coefficients have no reference point. So I need to have like a starting reference, right? I need to have a group that I'm always comparing to. The reason, there's a mathematical reason why I can't do it, because everything's a linear function of each other. What's really going on behind the scenes here is a bunch of matrix algebra, in which case we kind of break into some violations there. And if we had however many variables and they were all a direct linear function, we're going to have to leave one of those out, right? So, anytime someone is, for example, 54, right, that will be a 1. All the other dummy variables will always be 0. Anytime someone is 20, that will be a 1. All the other variables have to be 0. So we need to be able to have a regression where all of these dummy variables could be equal to 0. If I include every single possible age, that will never be the case, right? So I have to have one age category or age number here that I'm leaving out. And like I said, basically it's violating some kind of matrix algebra behind the scenes if we don't allow that to be the case. But I think a more intuitive explanation is, if I don't leave a group out, what would these slope coefficients be compared to what? There would be no base group. We have to have some kind of underlying comparison group. So if we go back to a smaller number, which was just these 3 different types of meats, right? Here now I have a base comparison, right? Now my slope coefficient is what's the additional weight lifted being in this racks category relative to the 0 group, or what group was left out, this group that was using this kind of excessive system equipment on multiply. Kind of think about, I'll try to give you another explanation behind this.
One of the regressions testing relationships
Mhm.
between multiple variables. So doesn't it make sense intuitively to include as many variables as you can, find the closest relationship? Why are we putting an X factor in that we're not accounting for when we have access to that data? That's kind of why I'm not getting why it kicks one of them out.
Let's see, I'll try to show you here. So let's say we had just very simple 2 variables, right? And let's say X1 was, I don't like to use this because I know it's politically not correct. Right, you can't belong to both of these groups, right? You're either 65 or younger, or you're over 65. Right? That's the only deal. So if I try to include both of these, so you're like, oh, well, I've got 2 things. But really, if I know that you're over 65, what do I automatically know? You're not younger. So this second variable isn't really providing us any additional information because they're direct functions of each other. So if I kind of thought about this, I know that X2 will always be, well, if someone's over 65, what would this variable have to be? So I know it's always going to be X1 minus 1. Okay? Or anytime, actually, I would want to think about, it's actually kind of the absolute value, right? Because then if this is 0, 0 minus 1, this has to be a 1. But basically, I know that anytime this is a 0, this is a 1. I could kind of substitute this in, and really I'm only including one variable in that regression. If they're direct linear functions of each other, by including both of them, I could really just rewrite this as that, and I'm really only including X1.
So It only kicks one out when it's dummy variable.
Yes, continuous variables are never, so it's only gonna be kicking something out if you have several dummy variables that cover like every single possible category. So for here, with every type of meat, every type, if I did do a dummy variable for every single age, then yeah, it would kick out one of those. But it's because I wasn't allowing age to be true and continuous, right? I was kind of putting it in as a dummy variable. So the only time it kicks out a variable, the only time you have this perfect multilinearity, excuse me, at least for the sake of what we're doing, it'll be if we were looking at dummy variables. Does that help with a little bit more insight? Like I said, if you can write one variable as a function of the other, if you try to include both, you're really only including one, right? And so then, you know, it has these coefficients, but you just want the coefficient just in X1, but if Stata can't display that to you, you know, you would pull out beta 2 minus 1 here, but Stata is the way it's, you can't just give it, that's not part of the output it can give you.
Yeah, I understand my comments. Can you go back to the data set real quick?
Yeah. So it says, it's basically said, okay, knowing that it's this additional third type, if I knew that it wasn't a raw meat or a meat with wraps, I know it has to be the other type. So including that in my regression, it doesn't give me any additional information.
Okay, I see. That makes sense.
Okay.
So it has to be one of the three, right? So if you account for two of them, it'll be that.
You automatically know the third. Because it has to be one of them.
But what if it is multiplied? Then how do you know what the coefficient is?
Yeah, so what would the predicted change if a multiply be? Well, it doesn't have an extra coefficient added in. What is its starting point? Just the intercept. So we had these,
So when we had these dummy variables, this is a good point. So we can think about this as when all the other variables are equal to 0. So with these dummy variables where we're thinking about, different, yeah, we're thinking about different groups. When all the other variables, so the only other variables were what? Male, age, body weight. When all those are equal to 0, what would the starting point be for a multiply meet? Well, 0 times this, plus 0 times this, plus 0 times this. If it's a multiply meet, these two are zeros. The only, the predicted Y value for that multiply meet would simply be that constant, right? So we would have the multiply meet would be kind of that starting point, right? That intercept, right? And now we can think about if we were trying to think of, okay, what about for the meat that allowed wraps? Well, once again, if all these are equal to 0, where's the starting point for that meat that was categorized as kind of using wraps? Well, it would be 109 pounds or kilograms, sorry, less than, but you would still get the constant added in. So it would be what? Negative 109 plus 207. So we're going to be at what? 99 approximately if we're rounding here. So it would be like, this is beta 1 plus, or sorry, beta 0 plus, and I'm writing 1 here, whatever the slope coefficient is on that other group. And then what about the category that was raw? Well, it would, once again, when all the other variables are equal to 0, if it's raw, wraps would be 0, so that would get added in. Here would be the intercept plus this slope coefficient. So that would be what? 87 plus 7, so 94. So when we have these categorical variables, the slope coefficients on the groups that end up getting included, it's not like it's changing the starting point, right? It's changing the intercept for that group. That's one way of thinking about it. But the group that just gets left out from my regression, its starting point will simply be the constant or the intercept, just that intercept coefficient.
Yeah, so initially I thought you had all the other coefficients up and then subtract from the constant, then that would be your multiply, I guess, in this case.
Yeah, no, so you wouldn't, it's only going to be, right? If it was a multiply meat, the raw and wraps category would both be zeros, so those don't get added in at all. Yep.
Okay.
Those are good questions. Other questions on this on the 14?
I went off script there a little bit, but I think that's good. this should be hopefully easy, but I'm trying to get some review in here as we go through this. If I wanted to test for which of these is statistically significant at the 5% level, which variables would you say are statistically significant here? This is going to have to be like hopefully a very easy question on the exam. You can answer this one, it's going to be rough.
All of them except age.
All of them except age, right? Because all we're doing there is comparing the p-value associated with each coefficient. Is it less than 0.05? Now, if I left off everything except for the confidence intervals, why do you know you could still make that same decision? Because the age confidence interval is the only one that includes 0, right? Or this is kind of like a not technical way of saying it. Like, I mean, it's technically correct. But anytime your confidence interval, the lower and upper bound have the same sign, right? You know that 0 can't be in that, right? You know you can reject, right? So anytime you have different signs on your upper and lower bound, you know that's going to be a variable, at least at that level, you can reject. Okay? All right. What happens is significant? Oh, well, once again, we already talked about this with the R squared and changing our sample size. But even if we're doing individual significance, I said kind of what's floating around behind the scenes with this standard error. So it has a numerator, but the key that we're going to be focusing on is that we divide by n-2 for these simple linear regressions. So if I take a larger sample size, what should happen to my standard error? It's going to go, the denominator here is larger. This fraction is, so this fraction would be smaller. If I'm now dividing by a smaller standard error, what's going to happen to my test statistic? It's going to go up. My test statistic goes up. What's happening to my p-values? And I should be more likely to reject the null. So we can kind of prove this to ourselves. I'll leave this up here for a second if people are writing down. If I ever move too fast, by the way, I'm switching back and forth and you want to see something here, always ask, all right? So here, if I compare this to when I ran the small sample size model, notice here age was the only one I couldn't reject. But if I run it without just using that small sample, I used all 84,000 observations or whatever I have, 86. Notice here, which ones can I reject? All these p-values, even the age one, right, goes to 0, right? Because that sample size is so high, it's driving my standard errors lower, test statistic higher, p-value smaller. I'm now much more likely to reject these. Sure enough, here I can reject all of them. Not only at the 5% level, but really whatever level I want. The p-value is always 0. So it really amplifies having 86,000 observations. Really amplifies the impact of having large sample sizes. If someone stopped in my office the other day, asked questions about like going out and working, getting data. There's tons of free data out there. The one that they came across that I always use as Kaggle. I don't know how I'm supposed to say it. But like if you can get data sets with like tens of thousands of like you're almost guaranteed you're going to be able to reject the null, right? And that's just because it makes sense. You have more information, you have more observations, so you have more evidence of whatever relationship you're finding. Right? If I only find a relationship from 20 observations, well, could have just had some extreme outliers in my data set there that really impacted. If I had an outlier or two in my data set of 86,000, that's not going to really influence my results that much, right? So kind of having that higher sample size, not only does it make it more likely we can reject with joint significance, but also much more likely we can reject when we're thinking about individual significance as well. Okay. Just to make this point as well. So I think the way that Stata does this, and don't hold me to this, probably Google it and see if I'm right. So notice it kicked out a different group here. Right? So instead of leaving out multiply, it left out wraps. So this is why, like, making sure, relying on Stata to do this is kind of okay, but it's probably best practice to choose the group you want to leave out, because the way that it chooses the group, I believe, is the group that has the smallest number of observations. So it just so happened in our smaller data set, we didn't have, the group that had the smallest number of observations was multiplied.
here it ended up being that RAPS category, right? And so, we allow state to do this, it's just gonna choose one that has the smallest number of observations. That might not always be what we want, right? But in terms of like the exam and stuff, you don't have to worry too much about that. That's more of like a working with actual data, what you want to think about. All right. Let me think if there's anything else I want to say here with this data set before we move on. Don't think so. So, are there any kind of general questions over multiple linear regression that you've kind of had over the past couple weeks? If not, I'll probably progress to looking at some of that practice exam and kind of picking some problems and kind of adding stuff in there. No? Yeah.
You exclude variables to avoid multicollinearity. How do you determine what the coefficient estimate would be of the excluded variable based on all of the other included variables?
So it would, so let's go back to this one, right? We left out multiply, right? What would, so the type of question that maybe I would ask is, relative to a meet that allows RAPS, how much more or less predicted weight lifted would it be if it's a multiplier? Well, that coefficient on RAPS tells you that relative to the multiply meet, the expected or predicted total weight lifted is 109 kilograms less. So how much more compared to the RAPS meet would a multiply meet you expect the total weight lift to be? Just the difference, which here, 0.109, so it would be 109 kilograms more. So it's kind of like the values really are already there, right? Because those coefficients are always comparisons to that zero group. So this coefficient you see is telling you how much less weight you could expect from these other categories. But that's the same thing as saying this is how much more weight you could expect from that category you're in. Is that what you were asking?
Yeah.
Okay. Any other questions? We kind of, like I said, jump way back to kind of early material here. Excuse me. All right, so, and let me see, I don't think I missed anything. I think we went through all this last class. Yeah, we did some of this stuff. Yeah, we went through this. Yeah, we should be covered all of this stuff. So let's go. Open up. And not put it on my OneDrive. No, it's here. So the files. Got my practice exam. I'll download it. Open it up. Right. So kind of notice, the bulk of this practice exam is really like linear regression stuff. So we're thinking about kind of going back to a lot of the stuff that we reviewed. I'm not going to be asking you like specific questions over kind of earlier stuff, but we needed to know things like what p-values represent. We need to know, thinking about what test statistics are. We need to know all of that and then lead us up into thinking about this regression material. So when you think about, we did review and cover a lot of things kind of that first week, first 2 weeks. We're really just setting us up for all the topics and principles we talked about with regression. So we'll see a lot of that pop up, and we're still talking about p-values, we're still talking about test statistics. But you can see from this practice exam, really what you should be focusing on is kind of that material, thinking about regression. Okay. So easiest, hopefully, we should be easy at this point. Probably slacked a little bit last week when we we're making more examples. But I talked through them a lot, so I don't focus on them as much, is interpreting these coefficients. Right? We're going to start out here with a very simple linear regression. Okay? So I've got percent of a county that voted for Trump in the 2020 election. I think it's percent, yeah. And then we have income measured in thousands. Okay? So on the exam, I'll give you some multiple choice. There'll also be some open answer. So these ones I have to phrase as open answer. Any question you see here, you can think about, I could turn it into a multiple choice, or any multiple choice question you can think about, I could turn it into a short answer. Okay? So if I wanted you to interpret that intercept, how would you interpret that intercept coefficient? So that's question 2. I'm kind of mixing out of order here just for a second. How would I interpret the intercept of that beta 0 coefficient? The intercept coefficient is always what? Yeah. Yeah, so it's the general form will be, it's the predicted y value when the x variable is equal to 0. So here it's kind of a weird one, but if the average income in a county was $0, the predicted percent that would vote for Trump would be about 20%, 19.97%. Now, that might seem kind of odd, like we know there's no county that has 0 average income, but there always has to be a starting point. So we said with these intercepts, that's still the way we interpret them. It's just that when we look at the actual data, if I'm looking at average income and I'm looking at percent that voted for Trump here, it could be, well, I don't know. We could look it up what the lowest average income is, actually, just out of curiosity, right? So Brown County, come on, let's do, I don't feel like doing the math. So annual. So it looks like Brown County has the lowest, Jesus Christ, average of $31,000, right? My God. So I think that's because there's not hardly anyone that lives there. It's like out in the middle of nowhere, but we don't ever see an income less than 31,000. So all of our data points might look something like this, right? However, if we do a line of best fit, the intercept is going to be all the way back here when income is equal to 0. So we still interpret the intercept the same way. It's just that in practice, we may never see any county actually be at that value for x, right? We may never see zeros in our data set, but that's still how we'll interpret it, okay? Okay, so thinking about that same thing here, I think I actually made the relationship opposite of what, no, it is. So it might not be what you expect. How would I interpret the slope coefficient? So what's the so the number there is 0.255. So what's the, yeah.
The change in y for every unit increase in that.
Yeah, so it's the predicted change in our y variable from every one additional unit x. So here's where knowing the general term, general way you interpret it, you want to have that. But when I'm giving you actual variables, we need to make the interpretation based off of the units and whatever these variables are. So here, it would be a $1 increase in average income. How are we told income is measured? Thousands. So 1 unit change would be for every additional $1,000 increase in average income in a county, right? We expect the predicted percent that vote for Trump actually goes up by about a quarter of a percentage, right? 0.255%. This is not what I would necessarily think. Can go into this, but higher incomes, actually we had those counties predicted a higher percentage vote for Trump in the 2020 election. And is that statistically significant? And at what level is it statistically significant? Yeah, the p-value is 0. It's statistically significant at all. Right? Now, why is that p-value? What's something that's causing our test statistics to be very large and the p-value to be pretty small in this regression? Got a really high number of observations, which we said drove down our standard errors, increased the test statistic, making that p-value likely small. Now, those are our interpretations, but why should I be maybe hesitant? What's something in that regression that tells me maybe I should be a little bit wary of this simple linear regression output?
Your R squared is quite low.
My R squared is 0.04. So what proportion of the variation am I not explaining in the percent of people that voted for Trump? 96% or the proportion 0.96, right? Remember, our R squared is always in terms of proportions, but we often very easily kind of go back and forth between percentages, just moving it back to place. Yep. So there's probably a lot of what important omitted variables that we have here.
Let me try to think of one off the top of my head. So what would, it's a really good one. Is that in the problems? Or did you just think of that? That's great. No, that is a great example. So let's think about this. So I ran this naive regression. So I ran this naive regression, right? And I only included income. So once I see that estimate, we saw it was positive, right? It was 0.255. Well, that's going to include the true effect, but also any important omitted variable. I'm also going to have bias that's now baked into that coefficient. So a good example, and I think it'll be good as we talk through it. If not, we can try to think of another one, but I think this will be good. So let's say I left out an important omitted variable, which was age, right? So here I'm thinking about the bias would have been, what would the effect of age been on the percent of the county that voted for Trump if I had included it in my regression? Times the covariance between income and age. And then this was divided by the variance of the variable I included. So that was income, okay? So on the exam or something, and I think there's questions later on, maybe I would give you kind of the output, tell you that covariance, run this second regression for you, and then ask you what kind of was the value of the bias. But here, let's just think about, can we sign the bias? So if this is the bias that exists in my estimate, right? My estimate that I see is the actual effect plus this additional component. What do you think the effect of age, if I had included in my, so as a county on average gets older, what do you think happens to the percent that voted for Trump? Older people tend to lean a little bit more right? Not physically, but right to the political spectrum, right? So if I had included it, I would imagine in any kind of poli-sci regression that you're looking at, age is generally going to increase the proportion that vote for the Republican candidate. That's not, I'm not breaking breaking news here, right? Now, what would the covariance likely be between income and age? As people get older, in general, what happens to their income? Yeah, hopefully, right? It's increasing, right? So as you accrue more, more skill, talent, on-job experience, you tend to see you have higher income as you get older. So the sign of our bias is going to be positive. So you can imagine, like, we saw 0.255, but what if the true effect was actually something like negative 0.155? Negative 0.155. What could have been the case is I actually just had a huge bias, right? Actually, my math's not mathing, is it? So let's say, well, to make this easier, let's say this was the actual effect is, what do I want? Negative 0.045, right? And then I had a bias of 0.3. Well, the actual effect should have been negative, but because I had such a large bias, the estimate I saw from my naive regression was actually this larger positive value. Right? So we can always put a sign to this bias as long as we can determine what do we think the relationship would have been between that important omitted variable and our y variable, and what would the relationship have been between that omitted variable and the independent x variable we included.
So a question like this is multiple choice. First of all, is the example?
So part of it is, part of it's not. If I'm going to ask you about the sign of the bias, because I'm going to grade it according to kind of what you tell me you think. Now, if I gave you output that told you the covariance, right? And I ran that second regression with the omitted variable included, I technically could then maybe create a multiple choice question. Maybe I ask you, what's the size of the bias? Right?
I don't think I have any of that in the practice exam for the Trump stuff. No, I don't. But I could do something like that, right? Where I give you what that covariance is between age and income. I run the regression where I've included age into it, and then ask you what was the size. And maybe I don't show you the original naive regression. And I say, what would be the size of your bias if you did run the naive regression and you left out age? Does that make sense?
Yeah, I'm just asking.
Big
Chance to explain our reasoning.
Yeah. So yes, if I asked you like just what the sign of the bias is, I'd be leaving it open-ended. If I asked you about the size, I'd be giving you additional information so that you know whether it's positive or negative. Any questions on that? I did kind of gloss over something here. Why didn't I put a sign next to my denominator?
Because you can't have negative income.
It's not negative income. Even if I had a variable there that could be negative, I'm actually, what's in my denominator is the variance. Variance is, we're taking that deviation from the mean and squaring it, so it's always positive. Yep, so we don't really have to worry about the sign. Usually I'm a little more complete. I say we know the variance is always positive. I just realized I forgot to say that, right? But that'll always be the case. All right. Excuse me. So let's think about, I think we've already talked about this one today. I think seeing it written out always helps. And that's just a matter of, we're kind of talking about the exam now. This will be the formula sheet. Also, I think I've mentioned this before, but just as we're getting closer and you're looking at all these materials, I don't know why. I kind of know why, but there's no solution to it. If you view things like this on a web page that I upload like PDFs, depending on the device you're using, there's compatibility issues. It's always a safe bet. So this one, I don't think there's any compatibility issues with this one. Like sometimes it'll like make things like jump all around and it looks all weird. If it ever looks like a really weird file, like there's something's gotten messed up, try downloading it, right? And opening it up as an actual PDF. Something about viewing it in a web browser, depending on what that web browser and what your device is, can sometimes cause some weird things with PDFs and even the Word documents occasionally. So a safe bet is probably always to download that. And I'm not doing that right now, so I'm kind of going against what I'm saying, but we don't have any compatibility issues here. So here's my kind of list of formula sheets I think we've ever made for this exam. And basically walking from where we started to where we are now. So you'll see here down at the bottom, we have that standard error. So we don't really do this in practice, right? We have kind of this sum across every single observation, difference between the y and the predicted y, we square that up. So that was kind of like our error squared. We then divided that by n minus 2 in these simple linear regressions. So that was where we said we could then think about my test statistic. And this was representing our standard error. But our standard error is the difference between y, predicted y, squared over n minus 2. I think the problem said if I took a smaller sample size, let's make sure I line up exactly what it's doing. Yep. So let's say I had a smaller subset of counties. So maybe I'm interested in making elections for the upcoming prediction. Or maybe I'm interested in making predictions for the upcoming election, right? And it'd be great if I had a bunch of data on all 3,000 plus counties, but I only have like 100, right? I can still make a prediction, but what's going to happen, right? Well, if I had a smaller sample size compared to what we were looking at before, what's going to happen to my standard error? So if I have kind of a smaller sample size, I'm dividing by, a smaller number, this will go up. If my standard error is higher, what's happening to my test statistic? If I have a lower test statistic, my p-value is, and I'm less likely to reject the null. So which of the following are going to be true if we only had a sample size of 100? Well, we said that our standard errors are going to be smaller. That was kind of one of the things we're increasing that denominator, as decreasing increasing our standard error. So we had a smaller standard error. Actually, no, we're not going to a higher standard. We're going to a lower standard size. Sorry. Yeah, we started out at 2,000, we're going up. So we had a lower sample size, right? Which made that denominator smaller than standard error. So it blew up our standard errors, right? So we have higher standard errors, so that one B can't be true, right? Our standard errors are higher. Because we have these higher standard errors, what's going to happen to our test is if we said it's going to be, that was our denominator, our test is it's going to have to be lower. So our test is to be larger, that one can't be true. The p-value associated with this income will now be larger. Well, we had smaller test statistics, so the p-value has to be larger. Right? So that one has to be true. Now I could have added an additional one in there, which is, and it would have to be wrong. So I'd have to say like, it is now more likely we can reject a null. Well, no, it's less likely with larger p-values. Now the reason why A is not true is because if you take different sample sizes, in theory, we could take 100 different samples, right? And even if they kind of vary slightly in size, they're all going to kind of follow a normal distribution. So if we were to take an infinite number of samples of size 100, infinite number of samples of size 1,000, we end up with the exact same average slope coefficient. So the actual slope coefficient value we see on income is unimpacted by our sample size. Now, in practice, when we have like one sample of 1,000, one sample of 100, it might look like it's different. But the theory is that if we were to take an infinite number of samples of size 1,000, infinite number of samples of size 100, they'll have a different variance. They'll be a little more spread out when it's a small sample size, but they're still going to be centered around what that true slope coefficient value should be. So A is not going to be impacted. Shouldn't change the size of our slope coefficient at all. Okay.
Any questions on that before we keep? So I think that kind of puts us right to the end of class here. Excuse me. So we've still got time to kind of get on and complete that quiz. I think I put up an announcement. There was an issue with some of the images. I got those fixed at the end of last week, so everything should be good to go on that. Problem set. So I think I have that quiz just before we end to make sure. I believe it's due by the time we meet. Or was it due today? Hold on. I might be mixing up my classes here. So we had, yeah, okay. The quiz is due at the end of the week, and I had the problem set due before we meet in class next Tuesday. Right? So start working on that problem set, get out of the way, so you can start thinking about kind of preparing for next week's exam. We'll have a lot of review, kind of be doing like we did today. So bring your questions if you have a chance to look at that practice exam. I don't want to just like work through them all. I mean, I want to do the ones that you guys have questions on. So bring your questions like, oh, what if you change this to that? How would that be different? So a lot of kind of more like active discussion over the next class here. All right. All right. We'll see you guys on Thursday.